experts. If people want to ask questions in either direction, please ask me questions as I go. Good. And so this talk is going to be about placing some old topics in a modern context. Old is really quite old, 50 years. In the case of this so-called BKL or Misner dynamics that I'll remind you about soon. And then arithmetic chaos is a subject that flourished in the mid-90s, early mid-90s. And so the modern context where I want to realize some of these ideas is holography, which I'll also remind you. Can you hear me at the back? Yeah, good. And now these old results are very well known and they're very well established, but they're not necessarily widely known, I think. So I'm going to spend a certain amount of time just reminding you or telling you about those because I think they deserve to be more widely known than they are. Everything I talk about is going to be in this paper that we posted a few months ago, including many more details. Marine is a postdoc in Cambridge, and George is my colleague in Cambridge. Good. So to remind you about black holes in the context of ADS-CFT or holographic duality. So it's very well established at this point that so-called eternal black holes, these are black holes with a positive specific heat. So in principle, they don't evaporate and they live forever. They have their Penrose diagram that looks like this. And so they have two sides, the right and the left exterior, and then two interiors. And this sort of geometric construction has a beautiful physical realization as the thermofield double state of the dual field theory, where the double corresponds to the left and the right sides of this Penrose diagram. And this connection was actually predates ADS-CFT, goes back to Israel in the 70s, and was given a sort of ADS-CFT context by Maldacena over 20 years ago. So the thermofield double state looks something like this. It means you sum over all the eigenstates of the dual conformal field theory, and you weight them with the Boltzmann factor. So this is an entangled state. If you trace out the left-hand side, you get the thermal state on the right. Since the last 20 years, there's been a huge amount of work on the exterior of this black hole and many beautiful gravitational phenomena. So this is the LIGO signal, such as the ring down of black holes. All of this happens outside the black hole, acquires or can be interpreted in terms of the dynamics of this thermal state of the dual field theory, right? In particular, the ring down, the last stages. I think you might just have heard a seminar about this now. I'm sorry, I didn't make it. This ring down at the very last stages, this quasi-normal mode ring down, has a dual interpretation as the approach to thermal equilibrium and eventually to hydrodynamics in the dual field theory. This has been a rich source of inspiration for the thermodynamics and hydrodynamics of strongly coupled field theories, which we wrote a book about a few years ago. So outside, there's still actually important questions, but we know a huge amount, and it's been very useful and productive. So today I'm going to talk about the inside. Okay. So the inside is tied up with lots of deep questions about an infalling observer. So if you could ask from this dual field theory point of view, you know, if you wait infinitely long at the boundary, you still only ever see what's outside the black hole. And so what is the interpretation in the dual field theory, which is supposedly a complete description of someone that falls through the horizon, and that's an infalling observer. Of course, you hit the singularity, and the interior can be thought of a kind of quantum cosmology. Say, if you think about these slices evolving in the interior, they're like a crunching cosmology, and there are many confusing things about that too, such as what are the right observables and so on. So the hope for at least 20 years is that the existence of this, you know, nice exterior might give you an anchor to try to address some of the conceptual problems in the interior. Okay, and that's the context, the immediate context of what I'm talking about. And recent developments, which are not what I will talk about, I'm just going to flash out these pictures to help locate some of you who might have seen them before, suggest that certain geometric aspects of the interior are encoded in quantum information theoretical facts about this dual thermofield double state. Okay. But before there's a sort of a logically prior question to asking what does the interior mean from the boundary. which is that, well, what should we actually expect to see in the interior? And even at a classical level, there's a problem. Excuse me, I'm hopping back and forth. I'm going to hop back one more time. The outside of a black hole, after some subtleties, is essentially stable. That means that if you sneeze outside the black hole, some stuff will fall through the horizon will get a little bit bigger, but it'll fundamentally look like the same kind of thing afterwards. If you sneeze here, okay, this future singularity is going to be completely different, okay? And that's because it's not surprising. The interior is a crunching cosmology, things get amplified, and the back reaction of a small perturbation is very, very big. So the interior of Schwarzschild is not a stable solution, even while the exterior is. This is something that, and there are many papers if you want to look at it, determined. Another way to say this, the Schwarzschild singularity is certainly not a generic singular solution to Einstein's equations. Okay, very non-generic. And so, for example, a perturbative analysis you can find in this paper. So the interior, even though the exterior of Schwarzschild ADS has been so useful, the interior is presumably physically relevant, certainly at sufficiently late times, close to the singularity, interior times, close to singularity. Just past the horizon, you're probably fine for a little bit, but eventually things are going to be unstable. Mathematicians are obsessed with this question. There's been a huge amount of work trying to characterize what the generic late time interior actually is. A lot of beautiful work that, as far as I know, the physical implications of this have been completely unexplored. In particular, the holographic implications have not been explored. And the question that keeps coming back to my mind, even though it may be a red herring, is whether these interior instabilities, which has nothing to do with the Lyapunov chaos and stuff, which is all about the horizon. Okay, it's nothing to do with the redshift of the horizon. It's stuff happening deep in the interior. Do they have any relationship at all to thermalization in the dual field theory? Yeah, possibly it doesn't. I don't know, but it's I can't help wondering. So, and finally, understanding actual generic classical interiors may be necessary before we try and understand quantum mechanical questions about resolving singularities, these kind of singularities. Good. So, my objective today is somewhat modest, okay? And I'm going to ask, again, sorry for bouncing back, what can we do to the boundary that in the simplest possible setting makes something a bit more generic happen in the interior? Yes.
So if you perturb inside the black hole, the singularity looks very different, but the exterior still looks strange.
Yes. It's all classical. So let me ask what, so of course you could just do a totally generic thing on the boundary. I mean, hopefully you should end up with something generic in the interior. That's too hard. Yes.
But if we're trying to understand the dual story, couldn't quantum mechanics be very important here?
Definitely, I'm sure it is. But immediately before it becomes important, we should have the classical situation under control. And so exactly how far you get before you have quantum mechanics is going to depend on how big, small L Planck is. Right? It might depend how big N is.
So there's some separation of scales.
Well, there could be, or there might not be. So, for example, for the black hole in the center of our galaxy, as I'll come back, you get 2 Kasna eras before you hit the Planck scale in our world. Now, in ADCFT, the Planck scale is a tunable thing. So I might have thought that by making N large enough, you can get as much as you want. But certainly for an actually existing black hole, how much interesting classical stuff you get before you hit the singularity will depend on how big the black hole is. The bigger the black hole, the better. Yeah.
And just in the context of the thermal field double, you don't have access to the future interior or the singularity unless you know the purification on the right-hand side or the left-hand side. And so it seems like just commenting on what you said that maybe it has to do with thermalization in the CFT. It seems like it would be more fine-grained information than thermalization because you actually have to know something quantum information theoretic in the CFT as far as what the purification is.
Can we come back to that later? Because I'm not sure I agree with that statement, but it may be a bit.
But just for the thermal field double, to be clear, not for a black hole function collapse.
We could think about a Godot experiment where the left and the right universes could talk to each other. Does that make it? It's a simpler mathematical problem.
Yeah,
it's just in here, like the entanglement wedge of the right is the right exterior, the entanglement wedge of the left is the left exterior. So if you're talking about thermalization, I would at least expect that you would only know those two. If you want to talk about the interior, you have to talk about the purification and the way they fit together. As marginals of some density matrix.
Let's chat around later, because in some ways, what I'm going to say is doesn't matter too much how this thing's realized, right? It's sort of a late time dynamic. Certainly, yeah, I'm not sure. So if I take the state and I throw something in, let's say somebody in this room, I mean, they're definitely going to experience some interesting stuff here.
I guess you would think that these two Kastner phases should be derivable from the dual.
Right.
Field theory.
Right, but only can access to both, to the full state, right?
Yeah,
As opposed to
definitely.
the-
That's good. That I do agree with. Yeah, it's the full. Sorry, if that's what, yeah, no, I agree with that. I'm sorry, I misunderstood. Yeah, that's what. I agree with that. And so these probes definitely involve things that involve both sides. Good. Okay, so right. So with that in mind, let's the objective is let's try to mess with the boundary in a simple way, not a generic way, because generic is too hard. You land in PDEs, which is why there are mathematicians studying this thing. Something that a low graph physicist can do that accesses that's simple, but nonetheless accesses some more generic behavior, more generic behavior into it. Okay. So the natural thing to do when you have a field theory is to deform it by a relevant operator. Okay, that's the way you can change a field theory and make it more generic. And so you can take our CFT, add a relevant operator, and does this more generic deformed quantum field theory have a more generic singularity behind its derivative double state? So we know how to do this very, very well. So I'm going to take this dual theory and I'm going to deform it as an action. And I'm going to deform it by some operator. For example, this could be a mass term in your mind. You're giving a mass to some of the fields. It has a coupling. And we know for a long, long time that what this coupling will do is introduce, there'll be a field in the bulk, and the RG flow of this operator will be encoded in some radial Z or Z. It's going to be my radial coordinate, and the coordinate will have some Z dependence, and that will break the scale invariance of the CFT, and that's your RG flow. These things are usually considered at 0 temperature, okay, where you flow from the UV to the IR. But something funny happens that you can certainly do it at non-zero temperature too. And something funny that happens is that the RG flow continues past the horizon where it develops in time. Okay, so let me draw this picture. So here we have a boundary. We deform something. We deform the boundary that modifies the space as you go in. The far infrared, the lowest energy scales, is the surface of infinite redshift. But the bulk solution doesn't care about that. It just keeps going. Okay, and this RG flow, if you like, unfolds in time once you go through the horizon. So our first attempt at this was a few years ago with Alex Uret and Darius, now a graduate student at MIT. And so the simplest thing you can do is you take your bulk, which is Einstein gravity with a negative cosmological constant, and this scalar field, this is just a free massive scalar field in the bulk, describes the renormalization group flow of this dual operator, right? Every operator has a scalar field. And so we do a very simple thing. You write down the equation of motion of this. It's just Einstein plus a scalar field. It's very simple. You make a simple ansatz. One of the things that's going to make this whole story tick is that in ADS you can have planar black holes, okay, which is sort of a bit simpler than the spherical ones. So these are the boundary directions, X and Y. Z is the direction going in, and T is time. This is simply the most general, and a couple of functions. This is the most general ansatz with the symmetry. Okay, it's the same symmetries as Schwarzschild ADS. Okay, so I'm looking for the back reaction of the scalar field on the Schwarzschild black hole, but I'm doing it non-linearly. I'm going to solve the full equation of motion. Just to show that you can do it, you get a bunch of ODEs you can put on a computer. From my point of view, it's practically analytic. It's very simple. I can do it on the computer. It's nothing very sophisticated. This is Z. Z is 0 at the boundary. This is the horizon. This is going towards the singularity. What I'm plotting here is the logarithmic derivative of various of the scalar field and some of the metric components. What I'm showing you in this plot is, just like in Schwarzschild, right? The coordinates just go through the horizon. If you want to be careful, you should go to ingoing coordinates and transform back and so on. But at the end of the day, you can just use Schwarzschild coordinates and it's all fine. The coordinates evolve. What these lines are showing you is that towards the singularities, the logarithmic derivative is constant, which means there's some power law behavior for everything. Okay. So what I've done, I've taken the boundary of Schwarzschild ADS, I've deformed it by a scalar, not turning on a non-zero scalar. It has some scaling dimension towards the boundary. That's the scaling dimension of the operator in the CFT. It turns on, it deforms the geometry, it goes through, and it deforms the singularity. And what I'm showing you here is that all quantities follow some various power law behavior. Okay. How?
What does that mean, deforming singularity?
So good. So just like very good. So in Schwarzschild, yeah, for example. All I mean is that so in Schwarzschild, I may be able to write it down. Let's actually these coordinates. Schwarzschild is something like this, and so here there's a square. So there's the horizon where GTT vanishes, the boundary where it's growing in the hyperbolic space, and the singularity is the behavior of this as z goes to 0 is the singularity. That's what I mean. So by towards the singularity, I just mean the behavior of this solution towards the singularity. All of the various metric components have a power law behavior. So that answers your question?
Yes.
Why is it so important that it be planar? I would have thought that spherical would actually amplify this even more. Because planar is one direction where things can die off, right?
So the thing about spherical, and I think, so something that we're going to do in a minute is embed this BKL explicitly in a black hole, to pose asymptotically. And to get the BKL, you kind of need to zoom in on the sphere and make it locally flat. And so this handout lets you go all the way from the boundary to BKL without having to flatten the sphere. Yeah, that makes sense. Is that a question, or is that I can? In case it's a question, I'm happy to.
No, I'm gonna fix it. Yeah, thank you.
So good. So I'll tell you what happens here. So here we land on a prehistoric solution of GI known as the Kasner universe. So
Sorry, can I ask one more question?
yeah, please go. Yeah.
So when you talk about deforming the singularity in this power law sense, is there a sense in which that maps to other notions of the singularity set, the way that Garrosh defined it as an equivalence class of geodesics? Like, is there an obvious sense in which that modifies that the singularity in that context?
I mean, I'm not familiar with it, but this is definitely a known singularity. I mean, it's not a I don't know. It's a short answer, but probably.
Yeah, but it probably maps in some way to or other to a definition of that.
Yeah, I would hope so. Because so this is 1921. Okay, not 2021. Right? It's a very, very old, one of the earliest solutions to GR that's known as this Kasner universe, and then later extended to include the scalar field by Linsky and Klandikov. And so I said the singularity has some scaling properties, which actually Schwarzschild already had. Schwarzschild is a special case of when you throw away these ones towards the singularity, right? Everything's power law, right? Okay. And so with tau the proper time for the singularity, the metric acquires this form and is characterized by these exponents. It's not the most general case because we have isotropy in these two directions. So the three exponents, the scalar field has this logarithmic running, and these powers, and only one of them is independent. We can take it to be PT. And so, for example, in this simple model, for a given deformation strength of the boundary, you get a different power in the whole. Right? So it has a one-parameter family of Kasner singularities. So every boundary theory has a different singularity, and Schwarzschild is here. Okay, so at the very least, this starts to show the non-genericity of Schwarzschild in the sense the interior, you make you deform the boundary, and the singularity also deforms. Okay? The fact that this exponent is negative means the time direction is growing towards the singularity, and the x and the y directions are collapsing. So in Kasner, there's always two directions that collapse, and the one that expand. But this doesn't have to be the case. Actually, there are other setups where PT could be positive. Okay. Right. So this is a simple instance in showing that Schwarzschild is the singularity is one point on a curve. And if you deform it, you land up somewhere else. Okay. Nothing special about Schwarzschild. So in particular, if you probe with the singularity, you certainly have no right. There's going to be an exponent, and it's not necessarily going to be the Schwarzschild. However, this isn't quite what we wanted. This is not the generic behavior. And a couple of years ago, Mark Hartnoll explained to us that the reason we hadn't landed on this more interesting chaotic behavior is that we hadn't have enough walls, which I'll tell you what a wall is in a minute. Now, chaotic behavior that I'm about to describe is conjecturally generic once all modes are turned on, including inhomogeneities. And everything I'm doing is homogeneous, okay, because I'm not a mathematician, are present. And so this is a conjecture. I think you had a talk about this last week or the week before. Yeah, that question.
Yeah, in the previous slide, so if we like kind of like deform a little away from Schwarzschild, do the like singularities look qualitatively different, or is it just a small?
So they're like this. So it's the scaling and the exponent changes.
Right.
Okay, whether, I don't know, but it's probably being, I'm sure this is classified in some, okay, it's you can call it hyperscaling by anything if you want. Right? There's not a scaling symmetry, but under a scaling, the metric scales by an overall factor. Like just a conformal filling factor, something like that. So the genericity of what I'm about to describe now, this chaotic behavior, goes back to this BKL paper from pure gravity and D+4, and more recently to Moore, Hartnoll, and Nicolai, considered higher dimensions, adding fields. And there's a very interesting fact that in the generic case, it's chaotic in less than 11 or less dimensions, which is rather intriguing. Okay, so now the objective in the remainder, this is sort of the warm-up, is to find a simple, so non-generic, we want to find a simple instance that nonetheless exhibits this more generic behavior. Okay, so I'm not going to look at the generic case. I'm going to look at a special case that I can solve easily, relatively easily, that nonetheless exhibits more generic class behavior. Okay. So that's what we did in this paper. And after some searching around, it turns out the simplest way to do it is to have three massive vector fields. Okay, so these massive vector fields are not fundamental, right? Their role in life is to realize the physics I want to realize in the interior of ADS in the simplest possible way. Okay, using ODEs. So if you don't like massive vectors, you don't have to be too upset, but there's nothing wrong with them. Okay.
But you couldn't have done it with scalars?
No. Scalars don't have the walls. And so it turns out that because there's an extra inverse metric in the kinetic term for F squared, that it really changes things, as I'm about to show you.
If you use a non-minimally coupled scalar, could you do the same thing?
Not very easily, no. Yeah. Because the thing is the scale, right? The reason vector fields are very nice is that there's a balance. So these walls are gonna, this cat gonna sort of block the Käsner motion. But whenever you introduce extra degrees of freedom, you get extra directions where it can escape. And so scalars, you might be able to add a wall, but then you also have an extra direction. What's nice about these massive vectors is that towards the singularity, the mass term will be irrelevant, and the Gauss law basically freezes them. And so these vectors freeze, they don't introduce extra directions, but they do give you walls that then block the metric components. And this mass is, yeah, absolutely not very essential, but it is important to get the exterior to work because we want to make them relevant from the boundary point and things you can turn on that don't mess up the ADS. So to get the exterior to work, you need this mass. But the thing I care about more is just a bunch of vectors. Yeah, so they're indeed they're qualitatively different from the scalars and near the singularity. But we're going to make basically the same ansatz. Okay, so again, the metric is basically the same as before, right? There's time, space, and the radial direction. And now each of these three vectors are going to give me a wall. We'll see what I mean in a second. And so they're going to have this. They're also just going to depend on one coordinate, and they're going to be in the dt, dx, and the dy directions. Okay, it's just an ansatz. It's a consistent ansatz. It's not the generic ansatz, but it's consistent. Solve the equations, and again, you get a bunch of ODEs. So the mass and the cosmological constant are both irrelevant towards the singularity. Right? When the curvature is big, clearly that term is going to be bigger than that term. And similarly for the mass, there are more derivatives here than here. But it's necessary to have a regular horizon with some boundary sources. And if this mu is small enough, the dual operator is again relevant, and so you preserve the ADS asymptotics and you flow it. So to begin with, it looks very similar to this, right? You have some sources, you turn on, you move them in. But once you start getting into the interior, different stuff happens. So the next part I'm going to show you is what this solution now looks like when you're over here. Right? So like this, yeah.
From the previous slide, so the ansatz that you're using for the vector fields, this means that in the interior, none of them are varying with the cosmological time.
No, they are only varying with the cosmological time. So in the interior, sorry, phi, and phi are functions of
Phi
Z.
is there, okay.
However, what happens, as I said to Andy's question, this mass term drops out of the equations, it becomes unimportant. So then there's a Gauss law for these terms, and so the flux that fundamentally
Right.
fixes them. And so there's a sense in which these don't do they get constrained by sort of a Gauss law in the interior, and they're more or less constant. But in principle, they depend on the cosmological time.
Just to clarify, the T in the interior is going to be a space-like coordinate.
That's correct. Yes, I'm sorry. I should have. That's right. Yeah, T is the time on the boundary, and on the inside becomes. Thank you. That's T. That's T. That's it. That's it. So now things start to look more interesting. And so what I'm plotting here are the three spatial components of the metric. Okay. To squeeze it all into one plot, it's double logarithmic on both axes. Okay. Right. So the numerics are trickier here. Okay. And that's why George Santos had to help us. Right. So things are varying over double exponential scales in both directions. But okay, that's what you get. And so what's happening, so each of these, it's a funny, if I was just using log axes, these would be straight lines. Okay, so these are these Kasner epochs, they look bendy, but I had to sort of squash them. And we're already past, this is sort of coming from the horizon, everything's nice. And these bounces are the bounces off the walls that I'm about to tell you about. So a Kasner epoch, so for one of these, in between a bounce, the three components of the metric evolve following the Kasner solution that I just showed you, but then these Kasner solutions abruptly end in a series of bounces. So a Kasner epoch is one of these. This language goes back to BKL. A Kasner era is a sequence of Kasner epochs that involve two of the metric coordinates changing dominance. Okay, so there's sort of one, remember, one is expanding and two directions are collapsing. And so what happens over an epoch is that it's sort of going like this. The two directions are involved, expanding, contracting, expanding, contraction. And then suddenly it's a flip to another two. Okay.
Can each of these peaks be identified with a wall?
Yes, I'm about to show you. Yes, this is about to show you. So this is just to show you that it's clearly different from what we got before and more consistent with what is expected generically.
Just another question.
Yeah.
So the number of horizons in all of these spaces is exactly the same.
That's right. There's good. Another nice thing about this mass term is there's no Cauchy horizons within this sentence. Yeah. So we know that's right. It's only So as far as I know, this is the first time that this kind of behavior, which has been known for 50 plots like this, not numerical plots, the kind of hand-drawn plots that look like this, are in the BKL paper. Okay, but we have a completely well-defined exterior, completely well-defined horizon, and this all within one ansatz. Okay, that's the main, in a sense, the main thing that we did. Now the walls, exactly. So another way to plot, so I should say, the leading near singularity equations, so the equations that are governing all this behavior, turn out to be identical to what's called the Bianchi-9 mixed master universe that Misner and BKL and others studied. Okay, so we're solving exactly the same equations. Once you're far enough in, the constant drop out, the mass drop out, and it turns out these three massive vector fields give you exactly the same walls as this Bianchi-9, which is the canonical solvable model, simple model for this. So let me show you what the walls mean. So it turns out these coordinates are not good everywhere, but near the singularity, you can use the volume of a spatial slice as sort of time. Okay, so look here, I have the volume e to the minus rho is outside of everything. It's the volume. Whilst h and g determine the shape of a time slice. Okay, if I take the determinant, spatial slice, it's this and this. If we take the determinant, there's an e to the minus 2h there, cancels with the h's there, and these g's cancel, right? So h and g are like the shape of the universe, and rho is the volume. So when you think of rho as like how the volume is like the clock, if you like, it's the time. And so here we have h over rho and g over rho. Okay, and then you come in from the horizon, and then this is the same evolution, or at least one of them is. There are several instances of the same evolution before. Now plot in these coordinates, and you see that what it's doing is bouncing around this triangle. And these are the walls. And they come from the kinetic term for the vector fields. So what this shows you, And as,
So just a qualitative question.
so, yeah.
So when it bounces off the wall, it takes a completely new slope.
Yes, and so as a, that's correct.
That's the chaos.
No.
It's forgotten its previous slope.
No, indeed, it's a fantastic question. So each bounce is deterministic and actually BKL derived, as I'll tell you. There's a reflection wall that tells you.
So it is a proper reflection. Okay.
Yeah, it's a proper reflection in hyperbolic space, not actually.
Yeah.
I'll get there in a second. It's a proper reflection. The chaos comes from the fact that it's a finite volume space. And it's a billiard ball problem in a finite volume. And so it's many bounces. So it's sort of the sequence of bounces that's chaotic, not any given one of them. Okay. And in fact, you can really get an analytic handle. In fact, BKL, I mean, this paper is completely amazing. So these Kasner epochs, you know, analytically, these bounces in the late time limit where they become very, very fast, you can also get analytically. There's overlapping regime mobility, you stitch them all together, and you can basically determine this whole evolution analytic. You have an analytic handle on this whole evolution. It's almost all in BKL's paper. Okay, so there we have it. So indeed, so BKL divide, I'm not going to go through it, but it's actually not too complicated. We write it, it's in our paper. Whether our exposition is better or not the BKLs, I'm not sure, but we convinced ourselves it's correct. And so it turns out that what really matters are these eras. Remember, an era is a sequence of bounces that involve two walls. Okay, and what they were able to get is the exponent. So remember, there was a PT, for example, right, which was the Kasner exponent for a given epoch. Okay, I'm going to tell you what this xn is. Okay, you take the first value of an epoch. So an epoch, remember. So the first value would be like, say, these three Kasner exponents, right? Would be the start of this epoch. Okay, there's a recursion relation that gives you this Kasner, the Kasner exponents here, in terms of the Kasner exponents there by solving each epoch. Okay, they got a recurrence relation. In fact, maybe I won't go through the details of that. It all boils down, essentially, there's a formula for P of n, the Kasner exponents, the nth epoch, in terms of a certain quantity xn. Okay. Is that set? Do you want to? So you parameterize, it turns out that it's nice to parameterize Pn, something like this. Same fault, it may not be 100% right, but it's more or less right. This UN is an integer part and a decimal part. So this is the decimal part, okay, and it's between 0 and 1. This thing obeys this recurrence relation, which is that in the n+1 era, you invert the xn1, and then you should, which is less than 1, this is bigger than 1, you subtract off the integer part to get something else less than 1. It turns out this is a very, very famous map, first studied by Gauss, okay, and it's the paradigmatic chaotic dynamical system, okay. So for example, here I've done a simple, maybe trivial, right? Actually you have to work to high many decimal places, but you start with xn, you revolve it over eras, and you know it goes crazy, right? You can then take all of the values that it took and bin them. Okay, these are the values. I've literally taken them all and just bin them. You get they follow a distribution, which is the equilibrium distribution. The ergodic property of this map. There's an equilibrium distribution, first found by Gauss. You know that equivalent to a trend, and it's this. Okay, so this is an ergodic map. It has an equilibrium distribution. Right? You can use that to learn a lot about the map.
But there must be special values of x which are not chaotic.
Rational ones.
Rational.
Yes, that's right. Which are very small number.
That's
correct.
Right.
So this is closely related, and the reason Gauss was studying it, to the continued fraction representation of your initial x. Okay, this is deep mathematical properties, but yes, so there are, it's the if you give it a rational value, it will terminate. Yeah. So, for example, this equilibrium distribution is reached very quickly. There's an equilibrium exponent, okay, that's like 1 essentially in reasonable units. And so using this equilibrium distribution, you can calculate a bunch of things about the late time dynamics. And for example, you can show, BKL showed, that the spatial volume, right, that's the volume of the slices decreases doubly exponentially over each era. Every era is a sequence of blobs. So the log of the volume expectation value on average in the late time grows linearly with n. It's not the number of epochs, it's the number of eras. Okay? Yeah? And this h turns out to be exactly the homogeneous Sinai entropy, essentially the Lyapunov exponent of this map. And you can just check that. Okay, here I've taken the orange lines, I've taken 300 initial values of x, evolved them, and I'm following, this is the logarithm of rho n, which is itself the logarithm of the volume, okay, of the universe as a function of n. And you see that on average, it's following this curve. Okay. It might look like there's a big variance here. Actually, there isn't. It's misleading. This is the variance of the volume over the log of the volume. And so the variance is going like one of the square roots. So it's actually getting smaller. Okay, so that there's a well-defined average of the late time evolution of the volume, and it's this double exponential pattern. This is where I get this for the black hole in the center of our galaxy. This gives you 2 eras before you hit the Planck scale. It goes down really fast. So good, perfect. Well, now we're going to get to the arithmetic bit in a minute. But so far, so it's been known for a long time that the approach to cosmos singularities is governed by a chaotic dynamical system. What I've given you so far is an explicit embedding of this in an ADS black hole interior. Okay, so if you want to try to discover the singularity in the boundary field theory, you shouldn't be looking for Schwarzschild. Okay, you should be looking for something more like this scaling. Okay, these should be the targets. These are better targets for a field theory understanding of the singularity than the Schwarzschild interior. These stochastic properties of the interior. Now, a further aspect of BKL that some of you may have heard about is at different points in space decouple. I'm not addressing that. Everything's homogeneous in what I'm talking about. Okay, there are 2 aspects of BKL. One was this decoupling of separate points, and one was this chaotic story. So in the last 15 minutes, I'm going to switch and talk about the same thing, but from a Hamiltonian perspective. And it turns out that really, it's even better. It's even better. Okay, good. So, any questions about what's happened so far? Once again, if you want to find the interior and the boundary, you probably want to look for some stochastic properties of this chaotic evolution. All right. Now,
So I have a
yes.
question.
Yeah.
I don't know the Gauss argument,
Yeah.
so it's new
Oh.
to me, but in that, what we have here in terms of what kind of randomness or what kind of underlies this chaotic behavior, since it's given recursively through this algorithm, is it fair to say this is a pseudo-random distribution?
Let's see, what would it's certainly not fundamentally random. There's an underlying deterministic equation.
Right.
Is that what
Yes. So, yeah, so it's not stochastic in
there's no
Physical
quantum
sense,
mechanics or
yes,
anything. Yeah. It's stochastic in the sense that there are nice rules that happen on average.
but it's not like, I don't know, arrival times of cosmic rays or radioactive decay or
No,
in
it's,
that sense, because it's algorithmically given, it could recur such.
That's right. If you had exactly the same initial, well,
It's not,
okay.
it's not so important. We can go on.
At this level, yes, that's right. I agree. And in fact, in terms of what kind of chaos it is, that this Hamiltonian perspective is going to make that even maybe more interesting.
How would you anticipate seeing this individual field?
I don't know how to see it. In fact, it seems really hard because all the interesting stuff is happening at exponentially small region. It's not only sub-ADS, it's exponentially sub-ADS. The thought that keeps coming to me is that maybe we should put it in the past and look backwards instead of trying to look forwards. Maybe that we should look at some Big Bang or
There's also the fact that what's quantum, like the dual is classical boundary, vice versa, or whatever. They have different.
yeah, well, the short answer to that, yeah, I don't know, but, yeah, I don't.
But at least in principle, we thermal field double state and deformed by relevant vector operators.
Well, that was to get the simple
That's
setting.
better,
Yes, this is
yeah.
one place where you could look for something, but
Right,
yes,
right.
indeed, that was indeed the objective, to give a simple framework where this behavior emerges. So you could try to look for it, but it seems very hard.
You might even need to make n exponentially large or something.
Yes, that n might have to be pretty large. Yeah, probably, that's probably right. Yeah, that's probably right. Now, there's one more structure to this randomness. So I'm trying to find clues, right? So I would hope exactly, the name of the game is to I'm reminding you, because most of this was known, about this structure that exists close to singularities. That is quite beautiful, and if it's somewhere in n equals 4 super mils, this is what we should look for. Okay, in the thermal field double state. Okay, let me tell you about the Hamiltonian. So so as you know, in GR, there's no preferred time. Okay, and the way that manifests itself is that there's a certain Hamiltonian that is 0. Yeah, and that's called the Hamiltonian constraint. Is one of the equations of GR, just like the Gauss law is one of the equations of electromagnetism. It's a classical equation of GR. Most naturally formulated from a Hamiltonian point of view, meaning, so I remember I had the metric, I had these formats G and H, which were the shape of the universe, and I had rho, which was the volume of the universe. When I did that, I'd actually already gauge fixed. I want to ungauge fix that and let omega be the shape of the universe. And all three of these are functions of rho. Okay, so this is the same as this ansatz. I keep the rho here, but instead of writing rho there, I write omega of rho. Okay, that's all. Take that ansatz, plug it into the Lagrangian. You calculate the conjugate momenta in the way you did in undergraduate dynamics. So these are the momenta. Right, it's a dynamical system. Everything's just a function. Rho is like time. There's one variable. You have these three terms. They all have their dual momenta. Right? And this Hamiltonian, I'll tell you what these are the momenta dual to the electric field, the components of A. These are basically the electric fluxes. Okay. And so the Hamiltonian constraint says that this combination of them has to be 0. Okay. Right, so it's in GR. So I've ungauge fixed. I've not chosen coordinates. I've relaxed my choice of coordinates by letting this be any function of rho. And then the way the GR tells me that it doesn't matter what I choose for rho, is that this constraint has to be in place. This is the remnant of being able to choose change rho coordinates. No preferred time. Right? Oh, it's very super explicit. Okay, this is the Hamiltonian constraint in this model. So this relates these three terms. And then at late interior times, Gauss's law, not the GR one, the electromagnetic one, makes all of these pi's be constants. Okay. So this is like a potential term, right? That has exponential potential for the coordinates omega, G, and H. So the way you can think about this is you're going to think of it relationally. There's no preferred time, so I pick a clock. I say, I'm going to think of the volume of space, the spatial volume as the clock. And I ask the question, what is the shape of the universe at a given volume of the universe, right? And so I think of the volume as the clock. And so I'm going to think of omega as time. That means that pi of h is the Hamiltonian that generates translations in omega, right? It generates shifts to the universe. So I take all of this and I move it to the other side of this equation. And I have the Hamiltonian that generates time evolution. Okay. In quantum mechanics, the natural thing to look at is the spectrum of that Hamiltonian, right? And this is an operator. Now, H, I think of time evolution. These are like momenta, so it's like two directions. G and H are like two directions, and it's a time-dependent potential. Okay. So again, yeah, hope that made sense. So I think of omega as time. I reorganize this Hamiltonian constraint as giving me a Hamiltonian for time evolution under volume. Chicha and Meissner did a change of coordinates, which is well known. It's even in the big textbook, big black book. You can change coordinates from omega, G, and H to tau, R, and phi. Why do you do that? So you see here, this is a time-dependent potential. It's a little complicated to work with. And so here, omega and g, which both appear in the exponent, you multiply them by a common term, and then you pull all the time dependence out. So the potential gets the form e to the tau times some function of r and phi. Well, then at late times, this becomes a step function, where this potential is positive, goes to infinity, and where it's negative, it goes to 0. And so what this change of variables lets you do, so tau is going to be the new time, and r and phi are like polar coordinates on this space of G and H, hyperbolic polar coordinates, okay? And at late times, in these coordinates, the potential becomes an infinite square well. And what you land in is a hyperbolic billiard problem, okay? So this is free motion. This is a potential that I'm telling you becomes an infinite potential in this late time limit. This means something very beautiful, that in this tau coordinate, the Hamiltonian generating late time evolution is time independent. It doesn't, in omega, I'm thinking about this as the Hamiltonian, it's omega dependent. The time dependent potential is an annoying thing. By doing this change of variables and going to late times, it just becomes an infinite square well. It restricts your variables, but the walls don't change. These are the walls, of course, that we saw before, right? These walls don't change at late times. And so the Hamiltonian becomes time independent at late interior times. Okay? That means that deep in this chaotic system that we just talked about is Hamiltonian. There's a conserved energy associated to it that emerges deep in the interior of the black hole. Okay, I feel this point is not, again, known, but maybe not widely known. So there's a time-independent Hamiltonian, which is just free motion in an infinite triangular billiard. Okay, which is also a well-known chaotic, classical chaotic system. Now, how do you characterize one of these Hamiltonians? If we were truly staying classical, a common thing you might look at are the closed geodesics. Okay, the lengths of closed geodesics are one way to characterize a chaotic system. A nicer way is to do a semi-classical canonical quantization, which means that you write down basically all that means is that p squared comes from the Laplacian squared. Okay, and then you get a differential operator on this triangle. So we've landed on billiard motion in this triangle. One way to characterize this motion, even classically, to solve the Laplace equation with these boundary conditions, the spectral data that you get contains all the information about the classical geodesics, for example. So there's a slight quantum shift here, but it's a pretty mild one. Okay? It's just semi-classical. So almost there. I've got this triangle. Okay, it's the same triangle that we saw before, but now I've got a Hamiltonian that determines the evolution on that triangle. The wave functions in that Hamiltonian can be decomposed into this is the hyperbolic Laplacian. So these r and phi directions. This term becomes a hyperbolic Laplacian in r and phi. Okay? And so the hyperbolic, so these are eigenmodes. And again, it's just undergraduate quantum mechanics. You have an infinite triangular square well potential. It turns out to be a triangle in hyperbolic space. It has a series of modes with a series of energies. You build a general wave function by summing over the modes, and they have some time dependence because it's time independent. It's a bit tangential. There's a slightly weird -1/2 here. That's upset. So some people have concluded that this means the wave function vanishes at the singularity, and it's just wrong because the right norm for this is the Wheeler-DeWitt norm, not the Schrodinger norm. In the Wheeler-DeWitt norm, this half gets cancelled. So the probability is conserved. Okay, so don't worry about this half. So one more time. So what we've mapped the problem to, this evolution, this chaotic evolution of the scale factors is equivalent to a billiard problem on the hyperbolic plane, and this turns out to be the billiard. Okay. Some of you may be more happy with the upper half plane, so the different ways to represent hyperbolic space. If you map this Poincare disk, so again, this isn't space, okay? This is the space of metrics, of superspace, right? The evolution of the universe is a bouncing trajectory in this space. If you map it to the upper half plane, it turns into this region. I'll tell you what the green region is in a second. At the moment, we're in the gray region. And these walls, it can be are the fixed points of these of certain reflections. This connects to your question that the reflections. There's a reflection group associated with this domain. This domain is blue. The billiard fundamental domain is the fundamental domain of a group called gamma 2. This is the principal congruent subgroup of level 2 of SL2Z. Okay, it's a subgroup of SL2Z that is generated by these transformations. We'll get SL2Z itself in a minute. SL2Z is the green. The green region is half fundamental domain of this subgroup, so that's a bigger domain. And in fact, the generic chaos is supposed to land you in the green domain. Okay? So speak about this SL2Z is a merge from Einstein's equations. Okay, there's no supersymmetry, no nothing, right? You just take Einstein's equation, you expand them close to singularity. What you land up with is billiard motion in the fundamental domain of a modular group. Okay, this just happens. Okay, now, you know, maybe it's a signal of something.
I have a question on the critical points. So are these points the points at which the different the different directions in which the scale factors are expanding or whatever?
No. This is literally the same triangle as before. So each bounce is a bounce off, and so an era is a sequence of bounces on between two walls.
Right. So at a critical point, is the expansion in the contracting direction, the scale factor, is that going from acceleration to deceleration? Is that what is happening, or do the two so there's one expanding direction and two contracting directions?
Yes.
So it's not that these two flip at the critical point, but just that both of them are changing from accelerating to decelerating.
So at one bounce,
At the critical point, at
what do you mean by the critical point? Is that a bounce?
fixed point.
So what do you mean by what do you mean by fixed points?
So the bounce itself. Right?
Yeah. So when you bounce,
Yeah.
at that point,
Yeah.
Yeah, indeed. So one of the expanding directions turns around and starts collapsing,
Oh, I
which
see.
certainly involves an acceleration, and the collapsing direction starts getting bigger again. Okay, I'm going to try to finish on time. Let me whiz you through a few things. So this is the domain. So chaotic billiard motion is chaotic. Billiard motion on these special modular domains is arithmetic chaotic. Okay, it has certain special number theoretic properties that mathematicians have studied that are quite interesting. Okay. So I'm going to go a little fast now to finish on time. Maybe just look at this bit. This is a subdominant. So the eigenfunctions, the solutions of the Schrodinger equation, if you like, in this domain are precisely the odd automorphic forms of gamma 2, where the oddness has to do with 0 along, because it's half the domain. That further breaks into different symmetry groups under this triangle has some rotation S3 symmetry, so you have to further break it up into these sectors. I'm going to show you results for one of the sectors, which actually corresponds to the fundamental domain of SL2Z. So, okay, so what I'm going to talk about today now are odd eigenforms, odd automorphic forms of SL2Z. There's nothing, these are not holomorphic, by the way, they're orthomorphic. So super quickly, the first thing you can look at is the density of states. This is how many solutions are there as a function of the energy, and it grows linearly. This is called Boyle's law, okay? The chaos is going to, this is, you can get this trivial, you know, in solid state physics, when you count the density of states, the same thing, okay? So that's a function of how many states are there at a given energy. You have to integrate over the momentum shell that gives you the energy. Okay, you do this, you get that. Okay. Also, we did some numerics. That's why George did some numerics on this problem. These are numerical. We found a few thousand solutions, and these are their energy. Chaos has to do about the small fluctuations about this average behavior. So the first thing you can look at is the nearest neighbor spacing. So here you look at the differences of energy. You have 2,000 energy levels. You take all the nearest neighbor differences. You scale them in a natural way. Let me not talk about it, and then you bin them. Okay. And what you get in this case is a Poisson distribution. What you're supposed to get for a generic chaotic system is a Wigner-Dyson distribution, okay, which has this level of form, the Wigner-Dyson. It's more like that, okay? And again, this is a classically chaotic problem, but it's quantum or it's arithmetic chaos. This is more typical of an integrable system. So it suggests there's some conserved quantities floating around, which in fact there are. And before I show you them, one more thing you can calculate that goes beyond nearest level spacing is the spectral form factor. And so here you sum over all the energy levels and you weight, you sum over all differences. So not just nearest neighbors, it's a richer probe than the nearest neighbors, right? Because you'll get all the energy differences. This is how a typical a typical Green's function behaves, right? When you look at a Green's function, it has the differences of the energy levels that matter. And so this spectral form factor is like a model for the differences. Let me be completely clear, this is not SYK or anything related to SYK. This is not a dual calculation. This is just gravity, okay? Just gravity, just metric evolution near the singularity. And so, okay, if you haven't seen this before, it may not be very illuminating. It has this disconnected part. And then the gray line, the gray is what you get if you calculate this. The black is what you get when you time average it over a window, okay, which is what you normally do with these things. 2 more minutes. This plateau, this has to do with the states being finite. This is the contribution when these are equal, goes to 1. The early times is just the Fourier transform of this density of states. Also not interesting. The interesting bit is a so-called ramp in the middle. Unlike SYK and things that you might have heard about in generic chaotic systems, you don't get a linear ramp, you get an exponential ramp. Okay. And this is also, I'm going to skip this, is also indicative of some underlying conserved quantities. So let me tell you what these conserved quantities are. This will be the last thing. The integrable-like features of this arithmetic quantum chaos that do this infinite number of so-called Hecke operators. Okay, and it goes like this. You have this region, right? And X and Y are the coordinates on the upper half plane. You're solving the Laplace equation. You just expand them in the basis of separable solutions, right? This is like a Fourier, it's like a Fourier decomposition. In fact, it is the Fourier, right? So it's sine in this direction. The wave function has to vanish here and here, right? So that's the sine of X. And then in this direction, you get a Bessel function, right? That decays.
Is one of those in N? Are those both in?
Yes, sorry, indeed. So each energy level is labeled by N, is a sum over M. Right? So when you fix energy level, that has some complicated form, and you do a Fourier expansion of that energy level. So you can suppress the N's in your mind. One energy level. So sine is a Bessels and a bunch of coefficients. These Hecke operators imply you can show actually quite easily. I've called it number theoretic voodoo, but it's actually not that complicated in a lot from a low tech. The voodoo bit is why it happens at 12, which I don't have a deep understanding of. But you can show that the non-prime Fourier coefficients. Okay, so this is a sum of the Fourier frequencies. The non-prime ones can be written in terms of the prime ones. Okay, so for example, C10 is equal to C5 times C2. Okay. It gets trickier when there are repeated primes. Okay, so for example, C9, 3 squared, is something like C3 minus C3. So I put this in quotes, so I might be getting a bit wrong. But so the tricky, you have a number, you can decompose it in primes, but the repeated primes are the source of the complication. And you get some extra terms, but it factorizes over primes.
Maybe C1 from this formula, or?
Sorry, the C1 is 1. Yeah, that's right, exactly.
Oh, no, I meant I'm over.
This guy. Yeah, so yes, exactly. So C9 is C3 minus C9 over 3. C1. So you're right. Yeah. Okay, so it turns out that these operators that do in fact commute to the Laplacian and preserve the boundary conditions, and they imply that these are not all independent, but they're given by the prime ones. I'm sorry, this really will be the last. One more minute.
Yeah.
Sorry, yeah. What these relations are equivalent to is the following. It's another way to package them. These L functions are like Riemann zeta functions. Okay, the Riemann zeta function, remember, is the sum over 1 over n to the s. You build this object, where you build this object out of the coefficients. Some of you may remember, Riemann zeta function has the property that it's the sum of all integers that can also be written as a product of the primes. That's why this Riemann hypothesis relates information of the zeta function to the primes. And so this is a sum of all integers. This is a product of all primes. And so only the prime, this is a way of encapsulating this package, these Hecke relations, okay? That all of the integers are determined by the primes. Okay? This object is very deep number theoretic conjectures associated to it and stuff. Okay. Absolutely final thing I'll say is that there's a conjecture which concerns at a given energy level, the distribution of its prime coefficients, right? So you've got an energy level. Yeah, these are just Fourier, these things are just Fourier coefficients, okay? That's all they are. It's just the Fourier coefficients of the wave function, right? They can all be written in terms of the prime ones. So let's take the first energy level, and let's calculate the first 600 prime coefficients, okay? So there's quite a lot of coefficients, they're quite high, right? It's a conjecture called the Sato-Tate conjecture that we have the most beautiful plot we ever saw, but it's consistent, which is that the prime coefficients are distributed. So these, you bin them. This is right. This is how many prime coefficients there are. So it's the value of these prime coefficients. They follow this big semicircle distribution, which is equivalent to saying they're drawn from a random matrix. Okay. And so this is sort of remnant of chaos in these. The spectrum is not really totally chaotic. It has integral-like properties. And each mode is essentially chaotic, meaning that these coefficients are drawn from a random matrix. Okay? So somehow there's a chaotic system in the far interior of a black hole, and these wave functions are connected to matrices. Okay, the coefficients of these matrices are drawn from a large N matrix. I find quite tantalizing that that's where it is. Okay, so general relativity in singularities follows chaotic dynamics with strong connections to number theory. This is a hint about the structure of quantum gravity. And I think it's quite interesting. There's time-dependent arithmetic chaotic Hamiltonian near the singularity, which may suggest there's some other dual description of the interior. It almost has a, with apologies, DSCFT-ish flavor, right? There's some Hamiltonian in the far interior of the future. So it's better because it's a legit Hamiltonian. Maybe there's a dual description, a different, not an exterior, an interior dual description. And also, this might be a very nice place to count black hole microstates. Because the microstate you can count on any slice, okay? But near the singularity, the slices have a particularly nice structure. Many directions, several questions about quantum corrections, obviously are important, and homogeneities, and then of course, we'd like to connect this all to the boundary. Thank you.
Thank you for a great talk. Are there additional questions for Sean?
I was expecting you to say something, or I was something. Do quantum scars come into this?
So there are papers. If you look at citations to the BKO, there are certainly papers of quantum scars in the title. And obviously there are some special geodesics, like the things that like bounce around like this and so on.
That might be the reason why those are nicer than I would.
But so I can say the connection has been made, but I did not extract anything useful from it. But there surely is.
Yeah, there sure is. Yeah.
Any other questions?
I'm thinking of this analogy to the billiards problem. Right? So as you said, if you just send it randomly, it will just exhibit some kind of a chaotic trajectory. But then there are special trajectories where it will just happily repeat itself forever.
Yes.
Right? In your problem, you're sending in some stuff from outside and asking, what does it do?
Yes.
I presume you can now design stuff that doesn't become chaotic, but actually becomes one of these regular measure zero kind of situation.
I mean, in principle, yes, but it'd be infinitely fine. So the initial data coming into this region involves solving a differential equation from the boundary data, right? And so I mean, I wouldn't know how to, yeah, I wouldn't know how to do it in practice, but in principle, yes. And furthermore, it's a good point. So it's a closely related, these closed, this arithmetic chaos, these conserved quantities, the way it manifests itself is, in fact, there are many more closed orbits than there would be generically. So if you take some typical triangle, there are a certain number of closed, you can ask, of all geodesics, how many closed geodesics are there with length L, at large L? And it turns out that because of these number theoretic symmetries, which makes a bit of sense, there's some kind of congruence between the edges, right? So you're sort of more likely to form a closed loop. They grow exponentially. So in fact, you can, an interesting quantity, an interesting fact that's related to this ramp is that there's an infinite degeneracy, exponentially large degeneracy of closed geodesics as a function of L, which may indeed should have some manifestation maybe from this boundary point of view. But it's hard to hit any given one.
Of course.
Did the arithmetic portion that you got depend on the matter content? that you
Yeah,
showed?
yeah,
Did
yeah.
you get
So-
some subgroups?
Yeah. So in fact, the claim is in actually not yet in BKL, but like in the early 90s, is that if you take the generic case, where what that means is that you have, let's say, pure gravity in 4D and generic initial data. And so there are a bunch of, you can actually, it's quite easy to read off what the walls are without actually solving anything. And you land in precisely the SL2Z one. So that's the smallest billiard. So not a subgroup. So in 4D, yeah, and in that's strange. Huh? And so what these guys, what Damore and Nikolai did is they took the different dimensions, and now it's no longer a triangle. It's like a higher dimensional simplex, or whatever the right word is, higher dimensional polyhedron that you're in, right? And the walls you get depend on the theory. Yeah, and the criterion for chaos is that you have a finite volume closed region, basically. And in higher dimensions, it's not SL2Z, but there are other algebraic structures that arise given by these polyhedral structures in higher dimensions. But yes, the walls depend on the matter content, right? So when we had a scalar, we had no walls, right? And so the idea of the massive vector was to find a minimal setting where you had enough walls to have a finite volume at late time evolution.
And exactly what happens when you go above 11?
Yeah, you land in a well, there are consistent Kasner solutions that just go on forever without bouncing. So it's like there's an escape from there's a direction where there's no wall, and you just go there, and so you just land. It's more like this story here. The reason this is all conjectural, it's not known. So in some cases, Kasner is a self-consistent lake time solution. In other cases, these billiards are self-consistent lake time solutions. But when you're looking at the full PDE, you don't know whether you found a self-consistent big class of solutions, but there might be a whole other lake times and then nonlinear equations, so you might end up somewhere else.
All right, so we should continue our lunch. Let's thank our speaker again.
Very inspiring.